By now, most people have heard of the one-way speed of light problem, a strange conundrum in physics which tells us that we cannot know the actual one-way speed of a light beam, but rather only its average round trip or two-way speed. Few are aware, however, that this problem leads to an entire class of theories dubbed anisotropic light theories, all of which reproduce the exact same mathematical predictions as the theory of special relativity, but none of which require that theory's invariance of light postulate. This in turn begs the question, given an infinite class of equivalent formalisms, how do we go about determining which one corresponds to the truth? This is Dialect with How the One-Way Speed of Light Problem Disproves Einsteinian Relativity. At the core of Einsteinian relativity lies the crucial concept of invariant light. In a nutshell, this concept tells us that an inertial observer will always measure light to travel at speed c in their own frame of reference, regardless of that frame's speed relative to other observers. This contrasts starkly with the classical picture, wherein for two observers in motion with respect to one another, you'd expect that if one observer measures light to travel isotropically at speed c in their frame, the other observer should measure light in their frame as traveling at c minus v in one direction and c plus v in the opposite direction, thus observing what's termed anisotropic light behavior. The problem with the classical picture, of course, began when such anisotropic light behavior failed to turn up in observation. Numerous setups, including most famously the Michelson-Morley experiment, were designed to test for such anisotropies. In essence, designed to see whether observers in motion with respect to one another would measure different speeds for light in their frames or not. And the results they returned were always null, meaning the speed of light always appeared to take on the same value, c, no matter what the respective speed of the experimental apparatus was. In 1887, the German physicist Woldemar Voigt proposed the idea of invariant light to explain these null results. And in 1905, Einstein reinforced this idea by suggesting that invariant light was an expression of a deeper relative nature of space and time, a view which today is still held by modern physicists. But there's a simple problem with such a view, which is that experiments like the Michelson-Morley one never actually measured the speed of light in the first place, as most people are led to believe. Rather, such experiments measured a related but not equivalent quantity termed the two-way speed of light. This means that a light beam was emitted from a certain location, then reflected back to that location, and its speed was only calculated afterwards as an averaging of the round-trip distance over the round-trip time. Meaning, since the more instantaneous or one-way speed of the light beam was never measured, such experiments left the possibility open that the outgoing light beam didn't travel at the same speed as the incoming light beam. Indeed, the only empirical fact ever demonstrated by experiments like the Michelson-Morley one is that the two-way speed of light is always constrained to equal c when measured with co-moving rods and a co-moving clock. But this in turn grants observers the freedom of assuming a wide latitude of outgoing versus incoming light speeds within such systems. For instance, an observer could assume outbound light in their system to travel at 3 times the speed of light, while inbound light travels at 3/5 the speed of light. And such an assumption would still be consistent with observation. Moreover, two observers don't have to assume light behaves the same way in each of their systems, so that one observer could assume one set of ingoing to outgoing light speed values, while another observer could assume a different set. And again, such assumptions would still remain entirely consistent with empirical fact. Thus, we can see that the possibility of anisotropic light was never actually ruled out by experiment. Of course, you might be thinking, well, gosh, instead of imprecisely measuring two-way averages using one clock, why hasn't anyone tried using two clocks to measure more instantaneous one-way speeds of light? Well, sure, that's a great idea, except for the wee little problem that measuring the one-way speed of light turns out to be, well, impossible, thanks to an issue aptly titled the one-way speed of light problem. Fundamentally, this problem tells you that if you want to use two spatially separated clocks to measure the speed of something, then you need those clocks to be perfectly synchronized. But there is in fact no empirical way to know whether any two spatially separated clocks are actually synchronized or not. Now, why in the world would it be impossible to know if two clocks are synchronized or not? Well, there are a number of subtleties involved in this problem which you can delve into elsewhere. But the essential gist is that in order to synchronize two spatially separated clocks, one must first send a signal from the first clock to the second clock, which communicates the exact time. But depending on the travel speed of the signal, there will be a certain lag between the emission and reception of that signal, which the clock on the receiving end has to account for. To properly synchronize the receiving clock, then, the speed the signal traveled in the direction of its trip must be known. But the only way to know such a one-way travel speed is to have already measured it using two spatially separated, perfectly synchronized clocks. We thus cannot sync two spatially separated clocks until we know the one-way speed of our signal. And we cannot know the one-way speed of our signal until we have synced two spatially separated clocks. This circularity demonstrates that the one-way speed of light problem isn't just some fluke of insufficiently thought-out experimentation. Rather, it's a fundamental uncertainty principle, a pivotal point of incompleteness baked into our epistemological framework. The philosophical implications of this are far-reaching, but at the moment it undoes something more immediate and pressing: the empirical legitimacy of Einsteinian relativity. That is, you're probably used to hearing that Einsteinian relativity is one of the most well-proven theories in all history. But in fact, it's never been proven at all, because its central postulate, the invariance of light postulate, is empirically unverifiable. Meaning, there's no way to know whether or not light always travels at speed c in each and every observer's frame. Indeed, Einstein, confronted by the empirical result that the two-way speed of light always equals c, sought to explain it by postulating that the one-way speed of light must also always equal c. Or in other words, Einstein claimed that the physical reality of how a light beam actually moves through space in any observer's frame should be equated to a two-way averaging of that movement, regardless of the context of the motion of the observer. To justify this, Einstein asserted in his 1905 paper that he believed that time could not be defined at all unless a given frame's spatially separated clocks were synchronized via assuming inbound and outbound light speeds to be the same. An assumption which, as we explored in a prior video, he felt was justified due to his philosophical outlook that time itself was reducible to nothing more than what clocks measure. That is, Einstein believed concepts like time and space referred only to how one should use clocks and rods to assign coordinates in any given frame of reference. To understand this a little better, let's consider that you're an observer located at the center of some reference frame, and you want to map out world events in your vicinity. When the time on a local clock reads t equals 0 seconds, you send out a light signal into your surrounding environment. And then at time t equals 10 seconds, that light signal returns to you, bearing information about the occurrence of, say, your nearby friend sneezing. According to Einstein's theory, your only option is to assume that the light signal you sent out spent half the total trip time traveling to its destination and half the total trip time traveling back. Meaning in turn that you are required to deduce that your friend's sneezing occurred at a distance of 5 light seconds away, when the time was t equals 5 seconds. The spatiotemporal coordinates you assign to the event of your friend's sneeze are thus 5, 5. Now, how you choose to assign coordinates affects what's called your notion of simultaneity. For instance, if you assume that light travels the same speed in both directions, then you may deduce that your friend's sneeze on your right occurred simultaneously to, say, your neighbor's dog barking on your left, because both light signals returned after 10 seconds. And indeed in this case, you'll assign both events the same time coordinate, t equals 5 seconds. But in the case that you no longer assume the instantaneous or one-way speed of light to be equal to its average two-way speed, although both signals still return to you at the same time, you can no longer assume they reach their destinations at the same time, and hence no longer assign the two events the identical time coordinate t equals 5 seconds. Instead, you may assign them a whole range of coordinates, based on whatever values you choose to assume for rightward versus leftward traveling light. As an example, say you assume rightward light travels at a speed equal to 0.75 c, meaning that, as constrained by two-way invariance, leftward light travels at 1.5 c. Well, because you know either light beam traveled a total distance of 10 light seconds in your frame, you know the distance out to both events still must be 5 light seconds. From there, some simple math tells you that your friend's sneeze occurred when the time on your local clock read 6.67 seconds. And similarly, that your neighbor's dog barking occurred when the time on your local clock read 3.33 seconds. Meaning, you now have judged these two events to have occurred one after the other. Ergo, by altering your notion of light behavior in your frame, you also alter your notion of whether any two given world events are simultaneous or not. This is called the conventionality of simultaneity. Not to be confused with the closely related concept known as the relativity of simultaneity. That concept refers to whether two observers in different frames of reference will agree on whether any two given world events are simultaneous or not. For instance, say you, your friend, and your neighbor's dog all fly by some second observer at a high velocity. Now, if this observer assumes isotropic light in their frame, then they'll perceive that your neighbor's dog's bark occurs before your friend's sneeze, since they perceive that your frame was moving towards the leftward traveling light. But if, as stipulated by Einstein's theory, you're also required to assume isotropic light in your frame, then you judge these two events to be simultaneous, because you assume you're at rest with respect to such light. Hence, you and the other observers' notions of simultaneity are said to be relative. Of course, if we move beyond the restrictive scope of Einsteinian thinking, then thanks to the conventionality of simultaneity, you as an observer can simply choose to adopt a new light behavior convention and assign coordinates such that your neighbor's dog's bark also occurs before your friend's sneeze. and in this manner align your notion of what is or isn't simultaneous to match the other observers. And in truth, you and the other observer have the freedom to do and assume whatever convention, whatever theory of light you best see fit. Now, of course, you may wonder how all these different light conventions could still somehow produce the exact same predictions. How could the laws of physics possibly remain unchanged if one goes about changing their simultaneity convention? Well, the key lies in the coordinate transformations that govern how different frames of reference map into one another. That is, in Einstein's isotropic invariant light theory, the laws of physics take the same special form in every frame of reference. But such physics only holds if you use the Lorentz transformations to go between those frames. In an anisotropic light theory, on the other hand, the laws of physics may take an altered form, but so too will the transformation rules required to go between frames be altered. Thus, though the laws of physics change in each different theory, such changes are always compensated by a corresponding change in the transformation rules, such that the total mathematics remains consistent. And it is this fact which, startlingly enough, disproves Einstein's special relativity altogether. How so? Well, it's because the theory of special relativity asserts that relativistic phenomena, like clock dilation, length contraction, or mass-energy equivalence, don't have physical or mechanistic origins, but are rather ultimately only a consequence of the unique space and time geometry that is encoded via special relativity's signature Lorentz transformation. But the Lorentz transformation isn't unique. It's only one among a number of space and time geometries we can choose, which will still give us the right answers. Put another way, special relativity asserts that all relativistic phenomena are a direct consequence of invariant isotropic light. But since each and every anisotropic theory also predicts these exact same phenomena, it would be just as valid to assert that they are a consequence of non-invariant or anisotropic light, as it would be to assert that they are a consequence of invariant light. Our reality, therefore, cannot be said to be a manifestation of a particular mathematical structure, like Minkowskian spacetime, if other mathematical structures exist which produce the same physical content. Now, since Einstein's theory makes precisely such an assertion, i.e. that its spatiotemporal geometry is both necessary and unique, it is thereby disproven by the existence of valid alternative formulations. To be clear, this only proves that Minkowskian geometry is not the cause or reason for relativistic phenomena, as the Einsteinian interpretation asserts. Now, what it doesn't prove is whether light behavior is truly physically invariant in all frames of reference or not, as empirically this is again impossible to prove or disprove. Which means, when selecting from all our possible theories, we must defer to some further criteria. But what precisely are all the possible theories? Well, let's go ahead and list them now. First, of course, we have the modern theory, that light is both isotropic and invariant in all inertial frames of reference. This theory is governed by the symmetric Lorentz transformation, and features relative simultaneity as well as observers disagreeing on whose clocks are truly running slow and whose lengths are truly contracted. Next, we have the class of Reichenbachian theories, where light is still invariant in all frames of reference, but now is assumed to behave anisotropically. These theories are governed by a corresponding class of transformations and also feature relative simultaneity and relative space and time. After that, we have the class of Sexl-Mansourian theories, where light is now no longer invariant, such that different observers assume different light behavior in their respective frames, which leads to a much more general class of transformations. Out of this class, there is a unique theory in which all observers agree on the same notion of simultaneity, and it is governed by this transformation. Now, in this theory, all observers agree on whose clocks are running slow and whose are running fast, and there are no weird symmetries or twin paradoxes to deal with. Now, there is still yet a further class of theories, because we must remember that how we assign coordinates is ultimately up to us, and that, in addition to having the freedom to assume different light behavior between frames, observers also have the freedom to assign coordinates via assuming that their clocks are physically running slow and that their rods are physically contracted. If they do this, it generates a further class of theories from out of which we can pluck a particular theory, the classical theory, which features the good old Galilean transformations, i.e., universal space and time. And so we see that nearly 150 years of experimental confusion has been in truth partially masked by our inability to understand our own measurement conventions. So, by what additional criteria then should we narrow these theories down? Well, this is where you have to ask yourself what you ultimately believe about what it means to do science. Do you believe, for instance, that it's truly scientific to equate the instantaneous behavior of a light beam to its average behavior? Or to assert that each and every observer should exist in their own unique measurement reality? Do you believe that mechanistic cause and effect explanations for phenomena like mass-energy equivalence, length contraction, or clock dilation, all of which follow very simply from classical wave mechanics, should be dismissed and ignored in favor of championing beautiful math and coordinative symmetries? Well, the channels of reason course through each and every one of our minds, so it's up to you to make a decision. But choose wisely, because truth is an elusive affair. This has been Dialect. Stay tuned.